Hello all, I'm Anjali Pandey, Assistant Professor in Department of Information Technology SKIT. I'm going to deliver a video lecture on the topic transactions and I'm going to discuss transaction concepts in which properties and model is going to be there, transaction states, concurrent executions, schedules, serializability, recoverable schedules and cascadeless schedules. So we begin with transaction concepts. So first of all, what is a transaction? A transaction is a unit of program execution that accesses and possibly updates various data items. You can simply define it as a single operation or a set of operations um, performing some logical unit of work. There are two main issues to deal with. First is the failure and second is concurrent execution of multiple transactions. Failures can be of many types like hardware failures and system crashes. Next is transaction properties, abbreviated as ACID properties. A stands for atomicity. Here we say that any operation or any transaction is going to execute completely or not at all. That is, if one transaction fails in between, all the operations done by that transaction should be rolled back at the initial state. Next is consistency. That means at the initial state and after the successful completion of a transaction, the state should be consistent. That means execution of a transaction in isolation preserves the consistency of the database. That is, if two different transactions are executing in isolation, that means they are not interfering in each other's work, then we can maintain the consistency of a database easily. Next is isolation. As I have just told you that there may be many transactions running concurrently. That means one transaction cannot interfere in another's work. So each transaction must be unaware of other concurrently executing transactions. Next is durability. That is, after the successful completion of any transaction, the changes made by that transaction to the database should persist even if there are some system failures. Next is our transaction model. The accessing of data by any transaction actually uses two operations, readx and writex. Readx is basically what we are transferring our data item from database to main memory, and writex means we are transferring data item from main memory to database. There is one example of a transaction written here. Now, how we can ensure atomicity, consistency and isolation and durability. These are ensured by some systems of our, or you can say system components of our database system like recovery system, concurrency control system. It's given in here. Next is transaction states. There are 5 states in which the transaction can be transited. First, active, then partially committed, failed, aborted and committed. Active means the transaction is being executed. It is in the initial state. Partially committed, that means final statement has been executed but the transaction has not been saved yet. Failed, that is after the discovery that normal execution can no longer proceed. Aborted, after the transaction has been rolled back. The transaction has been failed. Now it is being rolled back and we have entered in the aborted state. Then the next is committed, that is the after successful completion of any transaction. A transaction is also said to have terminated if it has either committed or aborted. Now, failed transactions has two options when it enters in aborted state. First, either we can restart the transaction or we can kill the transaction. This is how the transaction states or any transaction can be transited in different transaction states. It is been shown in the diagram. Like from active we can go to partially committed and failed also. Partially committed transaction can be failed at any moment, failed to aborted, and likewise partially committed can be committed also. Next is concurrent executions. If multiple transactions are going to run simultaneously in any system or they are allowed to run concurrently in the system, those are known as concurrent executions. There are two good reasons for concurrent executions. We can improve our throughput, we can use our resources in a much better way, we can reduce waiting time. Waiting time means a shorter transaction need not to wait for a longer transaction to complete. There are some concurrency control schemes through which we can achieve isolation with concurrent execution of the transactions. Next are the schedules. Schedules, as defined here, are sequences of instructions that specify the chronological order in which instructions of concurrent transactions are executed. It's nothing but a sequence of instructions which are going to be executed in different transactions. They must consist of all instructions of those transactions, and they must preserve the order in which the instructions appear in each individual transaction. Yes, a transaction that successfully completes will have a commit instruction at the last statement, and the transaction that fails will have an abort instruction. You can also say if there are a set of n transactions, there exist n factorial different valid serial schedules. So here is an example of serial schedule in which T1 is followed by T2. That means all the instructions of T1 are being executed first and then T2. There's another serial schedule where T2 is followed by T1. Next is schedule 3. Now this is a schedule in which the instructions or in which the transactions are executed concurrently. Now let's say previously in the schedules 1 and 2, the A plus B, the total value of A plus B is 3000. The ultimate values of after the successful completion of the transactions will also be 3000. Similarly, in here also, if we check, we are also going to get the sum A plus B as 3000. This is a concurrently executed schedule, not a serial one, but we are going to get the same consistent state. So we can say that this schedule 3 is also equivalent to schedule 1. So in schedules 1, 2 and 3, the sum A plus B is preserved. Now we go to the schedule 4. Here you're not going to get A plus B as 3000, you're going to get it here as 3050. That means you are going to get some inconsistent state. So you can say it's not a valid schedule actually. So now we deal with serializability. See, serial execution of a set of transactions preserves database consistency. This is for sure. Now, a possible concurrent schedule is known to be a serializable schedule if it is equivalent to a serial schedule. We are going to discuss it in detail. So, using the forms of schedule equivalence, that is of two types, conflict serializability and view serializability. So, before going to conflict serializability, we will first deal with what are conflicting instructions. See, there are let's say there are two transactions Ti and Tj with instructions I and j respectively. We say them to conflict if and only if they are both accessing the same data item q and at least one of these instructions is a write operation on q. The list is given here. Let's say I is read q, j is read q. So of course the read operation is there for both instructions. So I and j don't conflict. If it is a combination of read write, write read, write write, then they are conflicting instructions. So one of these instruction is a write operation on q. So read write read and write write combinations are the conflicting instructions. So what is conflict serializability? If a schedule S can be transformed into a schedule S dash by a series of swaps of consecutive non-conflicting instructions, then S and S dash are conflict equivalent. In a simple way, you can say the concept of conflict equivalence leads to the concept of conflict serializability. That is, S is conflict serializable if it is conflict equivalent to a serial schedule. Let's take an example. Here, two schedules are given: Schedule 3 and Schedule 5. Schedule 3 is concurrently executed, and Schedule 5 is a serial schedule. Schedule 3 can be transformed into serial Schedule 5 using some swaps like read B of T1 and write A of T2 can be swapped. Then read B of T1 and read A of T2. Write B of T1 with write A of T2. Write B of T1 with read A of T2. These are continuous um, swaps of non-conflicting instructions resulting into Schedule 5. So we can say Schedule 3 is conflict serializable. This is an example of a schedule which is not conflict serializable, as the read queue, write queue and write queue are all non-conflicting, are all conflicting instructions. So we cannot obtain either the serial schedule T3 T4 or T4 T3 by swapping instructions. Now next is view serializability. Here we define it as: let S and S dash be two schedules with the same set of transactions. S and S dash are view equivalent if the following three conditions are met for each data item Q. If in a schedule S, transaction Ti reads the initial value of Q, then in a schedule S dash also transaction Ti must read the initial value of Q. If, second condition, if in schedule S, transaction Ti executes read Q and that value was produced by transaction Tj, if any, then in schedule S dash also Ti must read the value of Q that was produced by the same write Q operation of transaction Tj. Third condition, the transaction, if any, that performs the final write Q operation in schedule S must also perform the final write Q operation in schedule S dash. Here nothing but the order matters. So here one example is given for read queue, write queue, T3, T4, T6. Three transactions are given, some operations are being done here. Here just see this schedule which is concurrent, which is actually following the concurrent pattern. This schedule is view serializable, and you can say that any schedule S is view serializable if it is view equivalent to a serial schedule. So this schedule is view serializable to serial schedule T3, T4, T6. But this is not conflict serializable, as the instructions are conflicting instructions. That means you cannot convert it into any serial schedule by swapping the instructions. You can also say every conflict serializable schedule is also view serializable schedule, but the vice versa is not true. Every view serializable schedule is not conflict serializable but has blind writes, that is write without read. Let's see in this example, T4 and T6 are writing the value of Q without reading the value of Q. So this is a blind write. Next, testing for serializability. It's a simple one using some precedence graph in which vertices are the transactions and edges are being formed based on one of these three conditions. That is, Ti executes write of Q before Tj executes read of Q. Ti executes write of Q before Tj executes write of Q. Ti executes read of Q before Tj executes write of Q. So the precedence graph for schedule 4 is given here. See, T2 is writing A before reading A of T1. So T1 to T2 has been formed. Similarly, write A and write A combination from T2 to T1. So T2 to T1 is also there. So it's simple. If a precedence graph for any schedule S has a cycle, then S is not conflict serializable. So you just need to check whether your precedence graph is cyclic or acyclic. Next is recoverable schedules. Actually, we need to address the effect of transaction failures on concurrently executing transactions. So recoverable schedule is nothing but if a transaction Tj reads a data item previously returned by a transaction Ti, then commit operation of Ti appears before the commit operation of Tj, then only the schedule will be recoverable, or else it will be not. Sorry. So let's take an example in here. Suppose uh, we consider that T9 is reading A and after that it immediately commits. So suppose T8 now fails. Later the read operation of T9. So now T9 has read the value of A returned by T8. So T9 is dependent on T8, and because of this, T9 must be aborted in order to ensure atomicity. However, T9 already committed and can't be aborted. Hence, it is impossible to recover correctly from the failure of T8. So to be recoverable, T9 would have to delay committing until after T8 commits. Else it will be a non-recoverable schedule. Next is cascadeless schedules. Before discussing that, we must need to know cascading rollback. A single transaction failure leads to a series of transaction rollbacks as different transactions are dependent on each other. Let's see in this example, as none of the transactions is committed, so of course this schedule is recoverable. But please see, T11 is reading value of A which has been returned by T10, and likewise T12 is reading the value of A which has been returned by T11. That means these transactions are dependent. So if T10 fails, T11 and T12 must also be rolled back. So it can lead to undoing of a significant amount of work. This is the cascading rollback. So now what are cascade schedules? Cascadeless schedules are considered as for each pair of transactions Ti and Tj such that Tj reads a data item previously returned by Ti. The commit operation of Ti appears before the read operation of Tj. As we say in the previous schedule, there were three transactions T10, T11, T12. So if T10 commits after writing A, then T11 read A will be secured. That means that cannot be a cascading rollback now. So that is a cascadeless schedule. So yes, every cascadeless schedule is also recoverable. So this is all about transactions. Thank you.